All right, so we're looking at two more tests today for infinite series to determine convergence. The first one's a P-series. It's usually pretty obvious. Okay. A P-series is this form. One over n to the p, which you've seen several of those so far, right? We're just generalizing it. Okay. P is a number, yeah, a constant. Okay, so this series converges if P is less than 1. No, greater than 1. Scratch that. Yeah, it's got to be greater. Yep. I don't know why I put less down. I was thinking geometric. Okay. So if I had this series here, we know it converges. Okay. Right, P is 2, we know that converges. Okay. And diverges all other cases. There's an example of a divergent P-series. What's P equal to in that case? Yeah. 1/3. Just remember you can rewrite that as n to the 1/3. Okay. So as the case with geometric series, where we had to rewrite the exponents at times, try to combine things, we're going to have to rewrite some exponents here. Okay. You could also write this as that as well, right? The properties of exponents will come into play here. Okay.
So divergence usually goes to 0?
Right. Yeah. Yeah, the terms here will go to 0, right? But it, quote, doesn't go fast enough to 0. That's why we have the divergence test, right?
But if it's 1 over n to 0, isn't it just 1 over 1?
Yeah, and what is that as a series? It's an interesting point. If P is 0, is that what you're thinking? That's just 1, right? What does that series do? What's the first term? Okay, what's the second term? And diverges, right? So, yeah, it's kind of odd to think that the terms go to 0. The sequence, right? It just doesn't go fast enough. Okay. Anything above 1 is where that actually starts to converge. Any p-value. Okay. So P-series very useful, just like the geometric series. Very easy to use. Okay. Good. All right. So that's P-series. Just the formula you memorize: converge or diverge. Right? At this point, you have that paper, right? So we'll make some memory cards here in the next couple days. All right. Let's look at what we call the integral test. It's actually pretty neat, to be honest with you. And first, what is a positive series? One of the conditions of the integral test is that a series is positive. So we have to make sure we know what that is first. Well, why did I do that? What do you think a positive series is? What do you think the terms do in a positive series? Yeah, they're all positive, right? So I already told you about alternating series, right? Decreasing series, well, this is just a positive series. So each term is positive. Okay. You can write that. Remember, we determine convergence of series by the partial sums, right? If you're adding the terms up, they're all you're going to add them all, right? There's no negatives there. You could also write it like this. The term is always less than the term after it because you're adding something to the next term, right? So here's another way to note that a series is positive. Okay. We could also say that series is increasing an increasing sequence. Okay. What if a positive series is bounded above? What do you think's happening? Yeah, the series converges. Right, so again, the partial sums are bounded above. That means we are converging to some number, right? Okay. And if a positive series is not bounded above, what's happening? Yeah. So if and that would look, of course, like that. Just keeps going. It never has a top to it. Never bounded above. So pretty, I mean, elementary. Think about it. Makes sense. Because that's basically the definition of convergence right there. Right? We're bounded above. It's positive and bounded above. We are convergent. Okay. So that's what a positive series is. Not one of your tests, okay, so just log it away as what is a positive series. And here is the integral test. Nice distance. Well done. Right. Okay. Okay, we have to change, first of all, we have a series. Okay. We have to make it a function to calculate the integral. Because remember, series are only defined on the integers. right? But integrals are defined on the real numbers. Okay, so if you'll remember the theorem from last week, the sequence versus the function, they function similarly. Okay, so we'll have to make this note. Let a sub n equal f of n, where f of x, the actual function in real numbers, right, is positive, decreasing, and there's one more condition, and continuous. Now, what's really nice about this test, if you determine that a series is, if this function is positive, decreasing, and continuous, you pretty much know you need to use the integral test. Because these are the only conditions that apply to this one. Okay. So, then, if the integral converges, right, 1 to infinity, okay, then the series converges. So really all we have here is an improper integral to calculate. Once you determine this is the test you need to use. Similarly, if the integral diverges, so does the series. Okay. Good. Good with that? I'll work you through a couple examples, and we'll be good. Let's look at this series. What did we call this series? Anybody remember? It's the harmonic series. Okay, we know what's P equal to. So we know that this diverges, right? So you would say since P equals 1, the series diverges. Right? That's it. You're done. The way we got to this point was to show this was divergent with the integral test. Okay. So before the P-series, the integral was the integral test. The integral test actually gives us the P-series. So in your book, if you look, the integral test will be first and then the P-series. I switch them because the P-series is just easier to do. Okay. So how would we show this is true with the integral test? So again, my hope here is that you would just use this as a P-series. But here's how to get to that point. Consider the function 1 over x, right? Is that function positive Okay, so again, considering x is greater than or equal to 1, because that matches here, 1 to infinity, right? Is that always positive? 1, yeah, it is, right? It's always positive, so we check, boom. Okay. Is this function decreasing? Yeah, you put 1 in, you get a half. 1, you put 2 in, you get a half. Then a third. Yeah, it's decreasing, correct? Right, so check. Now, could I show that with the derivative? Yeah, I could, right? But you don't need to. If you can look at that, you can see that it's decreasing. All you have to say is the function is positive, decreasing, and is it continuous?
Not at 0, but from 1 to infinity, yes.
On your domain. Yeah. I think all of you are. I could see it. Okay, so on the domain, yes. Okay. So let's just note that x equals 0 is not in the domain. Okay. Right, so all you have to say is since the function is positive, decreasing, and continuous, we can use the integral test. To show if this converges or diverges. Okay, and I'll let you catch up. How would I solve that? What do I have to do for improper integrals?
Change 2.
Yep. All right. All right, what's the antiderivative of 1 over x? Yeah. Forget the absolute value. And then we solve, right? So limit r approaches infinity, ln r minus ln 1. What happens to natural log as we go to infinity? So we diverge. Right. And you've just shown that. Therefore, the series diverges. Yes, you do need to make that. Your justification is made. You've shown that the function is positive, decreasing, and continuous. That the integral diverges. Now you need to state the series diverges. Okay, so then we're good.
What they ever specifically asked us to do a harmonic series for like the integral test?
No.
Alright.
There's very I'm pretty sure that you never, I don't remember on any exams it's saying use the comparison test to show that the series diverges. It will say, does the series diverge or converge? And you have to pick the test and do the work. Okay. There might be a case where it does say use the blank blank test, but I don't remember one. Okay.
You ever seen this on
What?
integral test?
The integral test does show up. Yeah. Yeah. Obviously, there are 9 tests that they ask you to know, so you're probably not going to have a couple of them on the test. Okay. But you never know what those might be. So one of their more popular questions in the past has been, which series converge? And they'll put, it's one of these 1, 2, 3 problems, and A will be this series, and B might be this series, and C might be, or sorry, 1, 2, and 3, 3 might be that series, right? Which two converge? Yeah, these two, right? So A would, you remember these problems, right? 1 only, 2 only, right? And you'll have to pick. Okay, that's a question where they'll load up like 2 or 3 different tests in one question. They're starting to go away from it because it's so time consuming. Unless it's basic like this one, right? So, but again, did they give you the test name? No. You had to pick it. Okay. All right, one more, and then we'll be good. Let's see here. So the function, there's our domain, right? So this is not a geometric series. It's not a P-series because of the +1. Okay, so we can't call it a P-series. But the denominator is always bigger than the numerator, right? So we know this is decreasing. So that clue, denominator is larger, makes me want to look at the integral test. Okay. So again, go through the easy tests first to see if it would work. Since they don't look at the denominator and the numerator and compare the two. Since the denominator is going to be larger, we know this is going to be decreasing. Okay. So. Is it always positive, the function? Yeah, on this domain it is, right? Because you just have positive numbers. Decreasing? We've already talked about that. Yeah, because of the squares at the bottom. And then continuous, right. Okay, so. Sure. Fun one. Okay. So, rewrite. Cool. Any ideas on how we're going to solve that integral? Yep. Betcha. What's our u?
X squared plus
What?
This time stuck.
Yeah, it's a long one. But, okay, du is then 2x, and we have to move the 2 over, right? All right, now we can sub. We've got 1/2 and du, and then we got 1 over u squared. And the rest of our junk, which is actually not junk, but. Do you guys want to change the Integrand limits? Right, if I put 1 in for x, 1 plus 1 is 2, right? It's not going to make any difference, I don't think, but it's just easier now. We don't have to change anything back to x's. We just remember to work in u. Okay, so what's the antiderivative here? Right? So that's u to the -2. So add 1, divide by that. So yeah, -1. Then we got our limit. Infinity. Which is. Oh, you. R. Sorry. I did skip that, didn't I? Romp. Good catch. What? All right then. Is that right? Yeah. Okay. What's the limit here? 0 plus 1/4. So this integral converges, right? That's what that means. You get a number, it converges. Therefore, the series converges. Whew. Yeah, they're long problems. Okay. Any questions? Yeah, the integral test is, it has the most conditions in it. So, just keep that in mind. The other tests, they take a lot of work, but it has the most conditions. Yeah, in that case, you would not be able to use a C-series. You have to use what's called the comparison test. We'll talk about tomorrow, but basically, you know what 1 over n diverges? 1 over n minus 1 is bigger than that, right? Because the denominator is smaller. So because of that, it's bigger, and the one beneath that diverges, it's going to diverge. It's called the comparison test. Okay, so
There's your homework.